Okay, so today we're going to cover chapter 10, which is perceiving depth and size. And I'm going to only talk about half of this material, just because we're sort of short on time in this semester. So when talking about perceiving depth and size, this is an illusion. It's commonly used, optical illusion, where looks obviously like the man is a tiny little man and the woman is pouring into his glass. And so when you look at this, it's a common type of illusion to misperceive depth and size, and it plays tricks on our eyes. But when we remove a key element, for example, the chair, what happens is you can really perceive the man's actual depth in terms of relation to the scene. And so this is an example of how we can be tricked based off of placement, based off of looking at one aspect of the scene versus another. And there's a couple of really neat things that we're unfortunately not going to really get into, like the Ames room, where it looks like the person is much smaller. You can put a baby in the room and a person in the room, and the baby can look 10 times bigger than the person based off of the placement and the angle of the room. But we're going to talk about some of the basic ways that we perceive depth in this lecture. It's going to be a little bit shorter than our typical chapter lectures. Okay, so let's talk about some of the cues that we use to perceive depth. So one of a couple of the basic cues that we use, for example, is one that we're really reliant on the image that's on the retina, and we are able to use cues to give us information on the size and depth of particular items in our scene. So the cue approach to depth perception is essentially how we're able to focus information in that retinal image and how that's correlated with the depth in the scene. So for example, when an object is partially covering another object, we know that that object that's partially covered must be farther away. And that is something that we use. That's a cue that we use called occlusion that tells us that there's depth. So if there's a partially covered object that's partially occluded, we know, okay, well, whatever is occluding it must be in front, and whatever is being occluded is in the back, and that gives us depth. And over time, through our experience in our environment, we learn to connect the cues that we get from our environment with depth. For example, with occlusion. Occlusion is something that we use after being in our environment for a period of time. And we're going to talk about some studies later on where if you aren't exposed to the right sets of cues, or if you have an issue with one of your eyes, how that's going to affect your depth perception, and you're not able to use those environmental cues to be able to perceive depth properly. So over time, we're learning these connections between the cue and depth, and then it becomes automatic. When you do it every day, all day, for all of your life, then it becomes one of those very automatic processes where you don't need to sit and think about it. So when we look at, for example, occlusion, and I'm going to kind of skip ahead just real quick here. When we get an image on our retina, for example, we have a tree marked by the T and the H marked by the house, and this is where it falls on the retina. We have no way of knowing how far light has traveled to reach each point. And so we have no information on the retina telling us the distance of the house or the tree here, right? So we have to rely on other cues that are going to tell us, what is this distance? Now, the placement on the retina just tells us that that where the image is, and it's the image on the scene here. But if you look here, there's no information about the distance between the house and the tree. So we have to use other cues to tell us distance and to tell us depth. And so we do this in three sort of types of categories of cues. We have oculomotor, which is based on two things. One is our ability to sense the position of our eyes, and the second thing is our ability to sense the tension in our eye muscles. And we're going to talk about these individually. We also have monocular cues, which is based on one eye, in cues that we get from of one particular eye, and then binocular cues, which are based on the information that we get from both eyes. And we're going to talk about monocular and binocular here in a few minutes, but we're going to start with oculomotor. So those oculomotor cues are based on two things. Convergence, which is that inward movement. When we have an object that's right in front of us, we feel our eyes start to cross. And so if we have, for example, our eye here and our eye here and an object right here, we're looking at this, well, our eyes will sort of turn inward to focus on that eye, on that object. So that's convergence, which is that inward eye movement where we actually can feel the inward movement. So if you cross your eyes right now, you can actually feel that inward movement. And I'm going to have you guys do an activity. So if you want to, pause and do the activity, that's probably a good idea. And then the second ocular motor cue is accommodation. This is where we can feel this happen, but the shape of the lens changes when we focus at objects of different distances. And that's the feeling of the tightening of the eye muscles. So you can look at, for example, you can put a pencil in front of you and let's say you have so find two focal points. So look maybe perhaps at a pencil or a pen right in front of you, and then something behind that, like on the wall. So you can feel, so if you focus on the object in front of you, like the pencil, you can actually feel your eyes sort of turn in, and you can feel that convergence. And then if you then focus on something that is behind the pencil or pen, you can actually feel the accommodation where your eyes are changing focus. You can also feel the convergence where that inward movement isn't there. So this is the activity that I want you guys to do, is just using your fingers. So I want you to take your finger, okay, hold it at arm's length, and then I want you to slowly move your finger toward your nose, and very slowly. And as you do so, I want you to feel your eyes move forward. You can feel the inward movement. So I want you, and this is going to be a journal entry, to describe the feeling in the journal entry. And if you feel any tension inside your eyes, you can also move from your finger to something behind your finger and see if you can feel the accommodation. You can actually feel the shape of the lens changing as you are focusing into something that's a little bit further from you. And then, of course, here, this is me an example of convergence where you're moving inward. Here, like the object is right here, and you can feel your eyes sort of crossing inward versus looking straight out at an object that's, for example, over here. Convergence is probably the most effective, is more effective, I should say, than accommodation. And it's most helpful up to about arm's length. And then as the object gets further away, we start using different cues. So that's just the basics of the ocular motor. Moving to the monocular cues, there are several that we use that are very helpful for us to be able to view depth. And this information is coming from one eye. So we still use accommodation, which is the same as we use for ocular motor. The shape of the lens is accommodating to focus on that nearby object. But we also use pictorial cues. Now, these are the information that we get from 2D images. So we're going to go through a bunch of the different ones that we use here. For example, occlusion, relative height. We're going to go into those in just a minute. But we also use movement-based cues, which is a source of depth information which is created by movement. But we're going to first go into these pictorial cues. So these are the information that we're getting from one eye from 2D images, for example, pictures. So we're going to go through each one of these individually, but just to kind of give you sort of a preview in terms of occlusion. So occlusion is when an object hides or is partially hidden by another object. But the issue with this is it doesn't give us precise information on distance. It just tells us that something's being occluded or blocked, that something is in front of something else. But like we used with this picture of the house here, it doesn't give us a lot of information on distance. It just tells us, for example, here that the tree is closer to us than the house. But we don't know if the tree is 30 feet from the house or if the tree is up against the house. We can't tell. So relative height, it goes on the principle where we know that higher objects appear further away. And if we look at the frame of a photo, for example, it's going to correspond to the height in our field of view. And so being higher in the field of view means that the objects on the ground appear farther away. And then being lower on the field of view causes objects in the sky to appear farther away. And I'm going to give you guys an example of that, where you can actually see that the base is on the horizon. It's all about the horizon, in which in terms of being above or below, and anything on the ground is going to look farther away. Anything on the horizon is going to look like the furthest point. And so we're going to talk about that in a few minutes. Familiar and relative size are all dependent on us having experience and prior knowledge of different sizes of objects. It requires us to be able to know that information ahead of time and have experience with that thing. I'm going to give you guys an example of an experiment that was done using familiar size. So the perspective convergence is all about thinking about it's like a set of railroad tracks, right? So railroad tracks here all come to the horizon, and that gives us depth. So it looks like, you know, that those railroad tracks are going further into the horizon. Atmospheric perspective is important for us in terms of looking at, for example, pictures of big scenes. Anything that's kind of blurry or hazy is going to look further away just because of atmospheric conditions. Texture gradient is really good for us to be able to determine what's in the distance, because things get more packed as they get further away. For example, marathon runners, if you look at a picture of marathon runners running down a street, the bigger objects are up front, and they're less loosely packed. And then people who are further away in the picture are going to look like little sardines packed in. And then shadows gives us really good information about depth, and we're going to talk about those individually. So looking at occlusion, we talked about that. When one object partially covers another, that gives us depth, but it doesn't give us much on distance. Relative height, and this is where I kind of explained before, that objects below the horizon are higher in the field of vision, that are higher in the field of vision are more distant, and then objects above the horizon and that are lower in the field of vision, visual field, are more distant. And so an example of this, I have a picture here that looks like, you can see here, two motorcyclists on a road and mountains in the back. So occlusion would be how this cactus is going to occlude this hill, which is occluding the mountain. And that tells us that the cactus is kind of up front first, so that's kind of the closest to us. The second thing is the hill, and then the third thing is the mountain. And that gives us information, again, not distance. We don't know how close these things are to each other, but we do know that they are, that whatever's being occluded is further away. Relative height, the far motorcycle here, as you can see, is higher than the closer one, and that tells us that that motorcyclist is further away than the one that's closer to us. Relative size would be that the far motorcycle and the far telephone pole are actually smaller than the other. So here you can see this telephone pole is closer, this one is further away, this motorcyclist is closer, and that. So if you're comparing this telephone, it's all relative, right? Comparisons. So if you compare this height to this height, you can say, oh, well, this telephone pole is closer than this one. This motorcyclist is closer than this one, because you're comparing the two together. Perspective convergence is where we see that the sides of the roads are converging in the distance here, and that's telling us that those are that this is further away, and that's the sort of more basing at the horizon points. Okay. And so that's what I just listed some of these. So we were talking about occlusion and relative height with the motorcyclist picture. Familiar size is based on our knowledge of that information. Relative size is if these objects are equal size, right, the closer one will take up more of your field of vision. Sorry, I kind of jumped ahead there. And then perspective convergence is where we see those parallel lines appear to come together in the distance. And this is another example of how we see perspective convergence, how they're kind of coming together for the horizon in the distance. And that's another thing we see with railroad tracks. Now, when it comes to familiar size, which I don't have, here it is, familiar size and relative size. So this particular experiment was done where participants viewed these coins with one eye. So here we have a dime, a quarter, and a 50-cent piece. And so most people know the size in relation to each other. So the dime is the smallest, the quarter is the next, and the 50-cent is the biggest piece. And so the participants were familiar with these coins. They were familiar with what size they were. And so what the experimenters did was they took these, pictures of the coins, and they shined a light on them, and it made it look like they were, big life-size coins. And so they had participants view these coins with one eye, and then all the coins were the same size. And so they had the people judge distances based off of their knowledge of the coins. And so what they did is they viewed the dime, for example, they viewed as, because they expected this to be smaller than the quarter, they said that the dime was closer than the quarter because or further than the quarter, because they said, okay, well, we know that the dime is smaller than the quarter, so therefore that affected their perspective. And so they were affected by their previous knowledge of that item. And said, for example, if the biggest coin was the 50-cent piece, then they would see that one looks like it is a different distance from the dime because it should be bigger than the dime. And so that's an example of how we use familiar size and how we know this information based off of our experience in the environment. So a few more pictorial cues that atmospheric perspective, which is distant objects tend to be kind of fuzzy and have a blue tint, because the further away an object, the more air particles and air pollution and dust and water droplets that we're going to have to look through. So for example, here, at this point in the distance, this part right here is really much fuzzier compared to this little bird right here that's staring at us. And so this appears much sharper, and this appears much blurrier, fuzzier, and also has a blue tint because of the atmospheric perspective. Texture gradient is where we see that equally spaced elements that are more closely packed as the distance increases. For example, here, this right here, they're in the distance and they look much more densely packed. Then here you can actually see spaces in between the individuals. If you look here, that you can see more detail, and you can actually see them and view them as being closer, whereas these individuals here are in the distance because they are more densely packed. And then we can also talk about shadows, which can help us in terms of by determining the blockage of light. The shadows can tell us where objects are located and also enhance any 3D objects that are in the picture. So for an example here, without shadows, we really can't tell where these objects are in space. We don't know. Is this one floating? Is this one floating? Is this one up against the board? We can't tell. So we don't know where these spheres are in relation to the checkerboard. We don't know if they're floating. We don't know if they're resting on a surface without shadows. And if you've ever looked at really poorly done art, for example, poorly drawn or poorly done cartoons, or very basic when they started doing different kinds of animations, if you look and you really start noticing when shadows don't exist, because it gives us so much information on depth. Adding the shadows will tell us where those items are located, where those things are. So you can really tell when shadows are missing because it's confusing in terms of relation to where the object is to other objects and where the object is to the ground. And so here you can see, this is very obvious with B here, that that this one is on the board, right? And it's starting to lift up. And so we can start to see shadows here, and that tells us that these spheres are going up and are starting to float. And without that shadow information, we really won't be able to tell where those spheres are located on the checkerboard. Now, shadows also enhance the three-dimensionality of objects. And so here we can see in A, this is what we would look at with, for example, early morning shadows. And many of you may have noticed, living in the mountains, you probably are very common. This is a very common thing that you see, where you're driving in the morning and you can actually see quite a bit of detail in the mountains. And so early morning shadows emphasize contours. So in this case, the mountain contours. But here where you can see that the sun is up higher overhead, that the contours are much more difficult to see. So it actually gives us a lot of depth information when the shadows are hitting, for example, in the morning. So those are the monocular cues. Now let's talk about motion-produced cues. So the motion parallax is when we see, it's one of the most important sources of depth information. And this is where we see close objects in direction of movement glide rapidly past, but objects that are in the distance tend to look like they're appearing more slowly. And you can kind of see this as you're traveling in a car, for example, where it looks like everything that's kind of in front of you is moving at a different speed than objects that are in the distance. And so this particular motion produced cue of motion parallax can be explained, for example, by how it is placed on the retina. So if you look here, this tree right here, if you look at the point that it corresponds to on the retina, as you move past this tree, it takes up more space on your retina than, for example, this house in the distance. And so this right here, this makes it feel like it's taking longer to move across your retina as compared to the house in the distance has a much smaller space that it corresponds to on the retina. So what it's going to look like is that the distance in the object is going to move at a different speed than, in this case, the tree. And so when we see that the tree's image is moving all the way across this part of the retina, for example, from point T1 to T2, okay, the house's image is moving a shorter distance, in this case H1 to H2, and that's going to change the distance and the speed at which we see things moving more rapidly. So the image of the tree travels at a larger distance across the retina than the house in the same amount of time. So it's going to appear that it's going to be moving more rapidly. And so this is going to change how we view that information in terms of, for example, if we are riding in the car or if we're moving across different objects. Deletion and accretion are, again, motion-based cues where we're seeing objects that are being covered or uncovered as we move relative to them. And so if you cover an object, that's just deletion, and then uncovering an object is accretion. And so we can do this during activity here. If you close one eye and you take your hands and you put them up in front of your face. So you're going to take your left hand and spread it out closer to your face. You're going to take your right hand, spread it out, but just a few inches away. As you look at your right hand, I want you to move your head sideways to the left, but you're going to keep your hands still. You're just moving your head. Now move your head back to the right. And what you're doing is you're able to see different different parts of your hand, and other parts of your hand are going to be covered up by your closer hand. And so what this is going to be a journal activity. It's a very simple one where you're just going to explain deletion and accretion about how you are moving your head to see different parts of your fingers, different hand. And so again, it's not a trick, it's not anything hard, it's just one for you to demonstrate how deletion and accretion work in that respect. And this is a pretty handy table to bring everything together. Each cue that we use gives us a best guess on object depth, and each cue is different in terms of how well it works based off of several different circumstances. For example, how close an object is, if it's moving, right? And so when we look at relative depth versus actual depth, there's a difference in terms of these cues and how we use them. So, for example, in relative depth, occlusion works really well for those shorter distances. In preceding actual depth, relative size, motion parallax, accommodation, and convergence work really well to in close distances to give us actual depth information. And so if we are looking, for example, at close range, accommodation and convergence work the absolute best. But as you can see here, there are other cues that we use. For about close to medium ranges, we're using motion parallax, we're using a deletion and accretion. And then for long range, we're really relying on things like atmospheric perspective, relative height, and texture gradient. But really, we're using all of our cues together, right? We integrate those cues together to give us information about depth. We don't just rely on just one. We, for example, use relative height when objects are touching the ground. We're using familiar size when we know the actual sizes of objects. But we do integrate all of these cues together when we are trying to figure out particular depth, because that's what's helpful for us to perceive depth information. So those were monocular cues. So we talked about here integrating the monocular cues. We talked about cues that we use in terms of if an object's moving. We talked about oculomotor cues. Now let's talk about binocular depth perception. So binocular depth perception is where we're getting depth perception that's created from input from both eyes. And we call this stereoscopic depth perception. And we're going to do a quick activity to kind of demonstrate this. So you're going to close your right eye. You're going to hold a finger on your left hand at arm's length. Then you're going to position one of your right hand fingers about a foot away so that it covers the other finger. So remember, you've got one eye closed, you got your right eye closed, so you're only looking at this with your left eye. And so you're going to cover the finger, okay, with you're going to line them up so that your left eye can see the fingers, okay? Now you're going to open the right eye and close your left eye. And I want you to see the position of your front finger, how it is changed relative to the rear finger. And think about how is this, why is this happening, right? So this is going to be a journal entry. Again, a very simple exercise to look at what's going on here. So when we're looking at the little activity that I had you do, this would be an example of where you started, right? So for your left eye, you have it open, your right eye is closed. So this is taking off the input from your right eye. And you've lined up your near finger and your far finger. So I'm assuming that you noticed that the near finger covered your far finger, right? But then when you switched from when you closed your left eye and you opened your right eye, what you noticed, I'm assuming, is that when you switched from your left eye to your right eye, you noticed that your front finger appeared to move to the left relative to the far finger. And so it no longer blocks, right? Because it's not in the line of vision the same way. It's not lined up the same way. So essentially what happened is your far finger has moved off of the fovea, because here we had lined up with your left eye. When you were just using your left eye, you have lined up the same place on the retina, so the foveas of the left eye were all lined up and it was blocking. Whereas when you looked at the right eye, and close your left eye, the right eye is starting to, it actually looks around the rear finger and you're able to see both, right? So it's in different places on your retina. And so you're using, you're able to take the image when you're using both of your eyes, when you open both eyes, information from the left eye and information from the right eye to give you two different perspectives on your environment. So we're going to talk about how we're able to see depth with both eyes, the information that you're getting from both eyes. And so a way that we can talk about this is the difference between, for example, 2D versus 3D. So 3D movies add stereoscopic depth information by being able to, so in this case, this is how some 3D movies work, or at least they used to work. They would take two cameras, right? So they would have a left camera and then a right camera, and they're slightly off in terms of perspective, right? They're side by side, so they're slightly off. And then what happens is that they film the movie with both cameras, and then they overlay the two camera images together. And so your 3D glasses has the ability to be able to see, for example, the left eyeglass lens can see the image from the left camera, and the right eyeglass lens can see from the right camera. And they usually do this by using polarized light. So they'll use light waves that vibrate horizontally here and vertically here. So then that will give us, the image that we're seeing, and we can only see from that particular image. And then when you overlay the images, notice that it's like double vision, right? So when you put them together, that gives you stereoscopic depth perception. And that's the same kind of way that your eyes are working in order to give you that 3D information. So another way that we can kind of talk about this is when we see, for example, people who have issues with the input coming from both eyes. So Stereo Sue is Susan Berry. She's a neuroscientist who's at a college who has had a lot of issues starting at a very young age with her eyes. She had her eyes were not aligned properly, and so she was reliant on monocular cues to perceive depth perception. So she used those monocular cues to perceive depth instead of using both of her eyes together. Even though she had had several surgeries to try to correct this, even into adulthood, she was a neuroscientist, so she understood the science behind using monocular and binocular cues and seeing depth perception. And it turns out that she realized as an adult that she was reliant simply on monocular cues until she was starting to do exercises. And so when a physician had her do different exercises to strengthen her eye, because what happens is in strabismus, what happens is in strabismus, my goodness, in strabismus, which is the alignment of the eyes, for example, having crossed eyes or having one eye that's like a lazy eye crossed outward or inward. What happens when that happens, your eyes are uncoordinated, and you will have a weaker eye and a stronger eye. And so your brain ignores the image of the weaker eye to avoid double vision. And so when that happens, that person is going to be reliant on monocular cues because they're only getting information or input in from one eye. And so with Stereo Sue or Susan Berry, when she started doing exercises to strengthen her weaker eye, she began to see in stereoscopic vision, and that was very very odd for her to experience that because she never experienced that in real life before. Kind of imagine putting on 3D glasses for the first time and seeing what looks like a 2D image, like a movie, start to jump out at you. She the first time that she remembered kind of experiencing this was when she got in the car to drive, and she said that the steering wheel appeared to be sort of floating out of itself, and she said it was just a very odd sensation, and she just wasn't used to experiencing that. And so what's really neat though is that this is how we view the world around us. This is how we understand depth perception, and these are the cues that we get. But she was actually able to experience it for the first time. And if you can think back to when you have, your first 3D movie or that experience that you have, that's what she experienced though in real life. But we don't really see that when we are looking around from thing to thing in our 3D world because we're used to it. That's something that we've experienced, since we've been born. And so it's just really interesting to kind of see it from that perspective. So looking at how we use these different cues, we rely on really binocular disparity, which is the difference in the images that we get from the different input. So here, for example, binocular disparity would be the two different angles of the cameras, and if you put them together, you can see that it doesn't overlap exactly, right? There's a little bit of difference between the two. So this difference, this disparity, can be described by how the images fall on different points of the retina, right? So I'll give you guys an example here. So we have Julie, for example. She's falling on different corresponding points of the retina here, right? They're corresponding. If you slide them over, it actually is the same position. But these corresponding points allow us to have a little bit of difference in the two images. And they make disparate images. They make two different images on these corresponding points that allows us to be able to get the information from both eyes. Now the horopter, this is this imaginary sphere that passes through our point of focus, where anything that's on the horopter is going to fall on corresponding points on the retina. So here, Julie falls, if you look at this blue dashed line, she falls on the horopter. So the tree falls on the horopter and Julie falls on the horopter. And so that is our focal point. Julie is our focal point. And so this is what we're looking at. And we can also make the tree our focal point, but this is what's falling on our horopter. This is that imaginary sphere that passes through our point of focus. Anything that does not fall on the horopter, right, is not on a corresponding point. So objects that do not fall on the horopter fall on non-corresponding points, and those make disparate images. And so when we look, for example, at Julie, if we are focusing on Julie, and let's say we have Bill here, okay, and Bill is sitting right here. Bill does not fall on the horopter, okay, and so he is actually not going to fall on corresponding points on the two retinas, okay, so that's going to cause disparate images, and we can actually calculate the angle between these points, which we refer to as the absolute disparity. So this is the degree to which the image deviates from the corresponding points. Okay, so wherever they're falling in terms of on the retina, we can actually calculate that angle. And then the amount of disparity between the two retinas, right, because they're getting two disparate images, that is going to indicate how far that, in this case, Bill is from the horopter. Okay, and that's going to be our angle of disparity. And it's going to indicate that distance. Now, the relative disparity is the difference between the absolute disparity of the two objects. And that's something that we can calculate. I'm not going to go into super detail about that, but that is something that can be calculated, and we can determine distance based off of that. So what you really need to know is the idea behind binocular disparity, that these are the difference in the images and the slight differences between the eyes, but we explain this by talking about how it corresponds on the two retinas. And if we were to slide the retinas on each other, we can actually see that these are corresponding points. And anything that does not fall on that corresponding point, that horopter, okay, is considered non-corresponding points. And we can actually calculate how far objects are from the horopter, and we can actually calculate the distance between the two objects by doing that. So those are the most important points from that. Now at this point, we've only talked about information in a geometrical sort of way. So we've looked at this disparity by, we can calculate this angle and this corresponding point. So we've talked about this sort of in a geometrical sense, looking at where the object falls on the retina and where that is in relation to the horopter. But now let's talk about this in terms of perception. So what is the person seeing, right? And so stereopsis, this is that depth perception that's provided by that disparity, that binocular disparity, the difference between those two images. And this has been done looking at the perceptual side of things with a few different experiments. Now, I'm only going to go into a couple of the experiments. We can talk about the monkey studies, but we're going to talk about a cat study, and we're going to talk about how we can use a stereoscope to look at this. So again, the point behind this, and we've talked about this over and over again, is it's important to look at, and I'm going to kind of jump ahead here, looking at the physiological side of things, looking at the perceptual side of things, and how is it that we're able to perceive it. So we can check if neurons are firing, but if the person says, I don't see that, it doesn't really matter, because the perceptual side of things means that the person isn't perceiving it. So you can have neurons firing and saying, this is what you should see, but if you don't see that, then that's a problem. So that's why we always have to look at these different relationships. The perception to stimulus relationship, stimulus to physiological relationship, physiological to perception relationship. We have to make sure that it all matches up for us to be able to determine that, yes, physiologically we can explain this, yes, we perceive it, and yes, it works together. And so one of the experiments that we're going to talk about is how we are able to actually create an environment where we have people relying solely on disparity, binocular disparity, and no other cues. And so in this case, what they did is they did what's referred to, they created a random dot stereogram. And the random dot stereogram has two identical patterns, but one is slightly shifted, okay? And so a stereoscope is used for the person. It's almost like when you get your eyes tested and you have like let's see if I can sort of draw this out here. You can have two different eye holes here, and you're actually looking at the two different eye holes. This would be the left one, and this is for your right one. And you're seeing this in, you're seeing the two images, right, simultaneously, but only the left eye is seeing this image and only the right eye is seeing this image. So you're able to provide a stimulus that is just to one eye, just to the left eye, and another stimulus is different just to the right eye. And so they create these random dot stereograms with these different patterns. So these, but slightly shifted. So when you look at the pattern here versus the pattern here, when you look at this with a blind eye, it's very difficult to tell that anything is different from one to the next. Now, if you sit and you look back and forth and back and forth and back and forth, you can kind of tell, okay, I see something's going on here, but I'm not quite sure what it is. The pattern on the left is slightly shifted 1 unit compared to the one on the right. And so the way that we can see this is actually looking at the actual matrix. So if you look here, this is the actual pattern that we're interested in. So if you look at this, so you see the A, B, and notice that this is three rows over, right? Well, now this corresponds to the pattern that's in this probably around this region here. Now, if we look here, okay, this is the same pattern here. And so each dot, each black and white dot corresponds to a 0 or 1, or X or Y or A or B, depending on what it is. And if you look here, so 1, 2, 3, 4 rows over, it's just shifted. It's the same actual pattern, but just shifted over slightly a row. Okay, so this part right here is just slightly different from this part right here. And you can see it much better here that it's shifted over to the 4th row versus this one is on the 3rd row. And so when you're looking at this, you're like, wow, there's no way I could be able to tell that. But when you present this image to the left eye and this image to the right eye, what happens is you're only using the disparity between the two images. You're able to notice it, and what happens is that the disparity causes the perception of a very small square to float above the background. And so that disparity between these two things right here creates this sort of little floating square. And so you're using no pictorial cues. You're only relying on the disparity to see that particular box float up. So that is a way for us to be able to determine, using the stereoscopes, right? So providing each image to each different eye, to allow us to only rely on disparity and to see, okay, well, we must have neurons in our brain that are specifically responsible for determining disparity and understanding that. And there have been other studies that have been done to confirm this, that yes, we have particular neurons that are firing just for disparity, binocular disparity cues. And as you can imagine, as we've been talking about vision for this entire time, that of course, as we look at different neurons, they are responding to different cues, whether it's horizontal, vertical, moving left, moving right, moving up, moving down, moving, in a different pattern. We have different neurons that are responding to different types of specific input. And so this, we were like, okay, this is confirmation that this is happening. But the problem is, and the problem is still continues to be, the correspondence issue. How does our visual system take these two slightly different images, one from the left and one from the right? Now, assuming that there's no problems with, that this is a completely normal functioning eye. There's no mismatch. There's no weaker, stronger eye due to a strabismus. There's nothing happening there. How is it that our eyes, that our visual system is able to take those two images and overlay them, not see double vision, right? And still be able to give us the right cues for us to be able to navigate our environment very fluidly without having any problems. And so how are we able to match these images? Now, it could be that the matches are made through the visual system by specific features of different objects. So a match is made based off of color or shape. If you look around in your environment, you can see that there's very unique objects that have different features: round versus a square versus gradient, textured versus not. Shadows versus no shadows, and different colors. How is it that we're able to match that up? Is it based on these particular features? Yeah, maybe, but it doesn't always work for all objects. For example, the random dot stereogram. Even though you're sitting here looking at the stereogram and they're very similar, if you look back and forth, it's hard, but you can't, it's not impossible to be able to see that there's differences there and be able to actually look at the details of the stereogram. So it's very difficult for us to explain this. And really, there has been no absolute satisfactory answer that has been proposed to explain the correspondence problem, to say, how is it that we're able to match these two images coming from each eye and be able to see fluidly? There have been psychologists, neuroscientists, mathematicians, engineers, a bunch of different people who have tried to explain this correspondence problem, and nobody has been able to come up with a good enough solution that says, yes, okay, must be what it is. And so going back to this idea that we know that there must be neurons that respond best to binocular disparity, right? And so we call these particular neurons binocular depth neurons or disparity selective neurons. And these are the cells that are actually responding to degrees of absolute disparity. So we talked about how you calculate the absolute disparity. We can actually create a graph, a tuning curve, where we're mapping out based off of the degree, right? So if we say this is the degree of disparity, and we look at the firing rate of a neuron, you can actually map out, okay, this tuning curve of correspondence. So in this case, 1 degree, 2 degree, 3 degree, and then firing rates, you can actually map out which neuron fires best to which degree of disparity. And so we can actually map that out into disparity tuning curve, just like we do with all those other different kinds of experiments looking at how specific cells respond to specific orientations and different features and different things like that. So it's crazy how this works, but there's really no explanation, even though we know that they're firing particular neurons firing specifically for different degrees of disparity. We're still not able to determine how our brains are able to take all this information together and really apply it to what we see. So looking at this sort of figure again, we talked a little bit about this whole idea of how we're able to create binocular disparity, and how that is allowing us to perceive depth in the case of, and we talked about stereopsis. We talked about the fact that binocular disparity does cause the firing of disparity selective neurons, and that we can actually test this, and they've done tests with monkeys and looked at different kinds of ways that we can stimulate, in terms of microstimulation, stimulate the different neurons to have the monkey perceive or respond to particular types of degrees of disparity. So that's where we see this right here actually happening, which is the test of the physiological side of things. And then finally, we're going to talk about this selective rearing. So we know that the disparity selective neurons exist. One reason, so we can look at microstimulation, but another reason why we know that they exist is because of the experiment by Blake and Hirsch. So if we eliminate these disparity selective neurons, we can actually mess with and ruin an animal's ability to perceive binocular depth perception. So Blake and Hirsch, this is the team that did the other cat experiments, where we saw that they selectively reared for having an environment that looks like they're in with just the horizontal lines, and then they had the environment where they're just exposed to the vertical lines. I said that backwards. These are the vertical lines and these are horizontal lines. And in some of the videos that we saw, you might have seen where they kind of joked, where they said that the cat was reared with an eye patch, right? Okay. So, this is like pirate kitty. So what they did is they put a patch on the eye of the cat, and for the first 6 months of life, they selectively reared for only the left eye or only the right eye. And so they found that, of course, as you can imagine, that the cats had very few binocular neurons, and they were unable to use binocular disparity to perceive depth because they lost the ability to use both eyes together. And so that tells us, okay, they eliminated the binocular neurons, they eliminated stereopsis, and so that means that disparity is perceived, or binocular disparity results from selective neurons that are responsible for stereopsis. And when you remove those neurons by, for example, selectively rearing cats who only can see from the left eye or from the right eye because you've patched the eye, then that tells us that those particular neurons are responsible for that kind of vision. And so again, this is just a physiological perceptive connection that we can use to say, okay, something is explained by what they did in that particular experiment. That the binocular disparity is obviously a result of these very selective neurons being able to determine that the images are coming from both eyes. And so if you have any questions about this particular material, please let me know. But I know that there's more slides in this PowerPoint, but we're just kind of stopping here because that's the bulk of what I want you guys to know for this material. So if you have any questions, let me know. And this will be on the exam that's going to be up on Moodle very soon. So have a great day, and we'll see you next time.